I did some very crazy thing, which is somehow I made it like to operate over 6 months. And we sometimes have classes which are not even on the scheduled time. Or sometimes extra classes, or I change the times or something like that. So.
Okay. Yeah. So is it getting warmer in Kanpur now? In Pune, it's quite warm already.
Yeah, same here. I mean, it's pretty surprising. It just doesn't get so warm. Like, it's like maybe the end of March, or like maybe the second week of April it gets somewhat warm. Now it's like even like last week of Feb got very warm. So it's I don't know, is it global heating or because I was talking to some of my like colleagues, even other parts of the world, and they were also saying it's become much warmer there than last year.
And then you have this unpredictable things like in Austin and Texas area. There was a huge
it snowed and all. I mean,
so
weird.
you know it's snowing in the desert, so so something is wrong somewhere.
So we used to like see all these science fiction movies where there is a like 2012 and all. There's this climate change. So now I after this COVID thing, now I can see anything just can happen.
Correct.
So I can't. So because I mean there was like so many virus movies and all. There is a virus, and people are zombies and all that. And I mean something like this COVID thing was such a big realization. Then things are so flaky. I mean, within a month or so, things can just change drastically.
Yeah, I think forces of nature are much stronger than what we give them credit for, and even a simpler event like a volcanic eruption can cause long-term weather pattern change for like 3-4 years, right?
Right.
So I think
now I'm looking forward to the other science fiction things. Maybe time travel is possible soon. Maybe.
Yeah.
So now I stopped watching this. I used to really enjoy these movies, these virus movies, and where people are struggling. And now I hate looking at those movies. Now I stopped watching all this.
Yeah.
So I think we already have close to 60 people, and I think we have a big rush in another couple of minutes.
Okay. So how are you at IIT managing labs and things like that? People are able to do things online
so that is the thing. So what we are trying to do is that we have tried to play with the template so that the more theory courses can be done at this point, and the lab courses can be shifted. So CS doesn't have that big a problem because mostly you need a laptop, and most students do have a laptop. But the other departments are facing a bigger problem because they have a bigger setup. And so what they have tried to do is move the lab courses around and bring in the theory courses first so that they can finish off some things at least. And now we are calling some students in batches. Like for example, the final year students are coming next month, rather this month. And so they can now do the labs and stuff like that. Or maybe over the summers they can do something. In fact, we have a very weird situation now because of this COVID thing, the JEE admissions got delayed. The admissions got really delayed, and I think this particular batch actually joined in November instead of joining in somewhere like in July. And because of that, we have this very weird staggered semester. So now there are 2 semesters running at this point in time. There is the second semester and the first semester is running together, depending on which year you are. So the first semester for the first year students would end this month, and they will sort of immediately start with the second semester. So it's sort of crazy for them. So they are trying to push 3 semesters in the year, so that sort of getting.
I think the holidays would be.
Holidays are gone. Absolutely. and even the faculty are they are also having these issues because now they are not teaching for like 2 months and suddenly there is a course, and then so it's like figuring when scheduling the courses becomes tougher. So I think maybe I'll give another minute. So I think maybe once we have close to 100 students, we can start.
Yeah, sure. So on the flip side, though, one good thing is that all conferences being online, I think it has really increased the accessibility to information, and also many of them are free and or with much reduced costs, and so that's a positive thing.
That is sort of true. But the problem is that like attending a conference like offline is, I mean, you don't get the same feeling.
Yeah, that's true.
Like initially I was very excited and I ended up registering for everything that was there, and I attended none of them. Because it was always, the video will be available, so I will look at it later. So, in fact, I forgot registering for like one of the conferences where I had a paper, and I even forgot registering for that. It became like, finally it was like, what's the point? I'm not going to attend.
Yeah, I think being there in the moment has something that is kind of irreplaceable.
Yes, and you were there like for 3 days, and you're talking to people, talking about the same thing. That gives a very different environment to like being here. Like you are like shuffling between one meeting and then a talk somewhere, and so, so I think maybe we can get started. I think we have already 94 students.
Okay.
So I think maybe we can try sharing the screen. I think it should work out.
Okay.
So guys, I'm really happy to have Deepabran with us. So he's the director of compiler software at NVIDIA, and is passionate about building compilers for GPUs, CPUs, all type of compiler and other types of compiler technology-based solutions. So he has been working in the field of compiler development for more than 20 years now, and he has worked on retargetable compilers, hardware software co-design, dynamic binary translations, high-level synthesis, and most extensively like being in NVIDIA on GPU compilers for compute and graphics. So he has several patents in binary translation, high-level synthesis. Like he's always excited to meet people on the road, and engage with them, talking about compiler technology. So I can share you his details. I wanted you to see him first, so that's why I didn't do it earlier. Many of the things I told you, like I talked about retargetable compilers, hardware software co-designs, binary translation, maybe they don't make sense to you right now. And this is the opportunity that you should be asking all this. What is all this business? We didn't understand any of that. So he's here to like answer all your questions now. So make the most of this opportunity. So this is really great that he has taken some time off to share his like extensive knowledge with you guys. So like over to Deepabran.
Yeah, thanks Shubhajit. Before I begin, are you able to see the full screen view? Can you confirm?
Yes, I think it's visible.
Okay, so you don't see the presenter view by any chance, right?
I just see your video and I see the screen. That's it. Yeah, the screen which says applications of compiler technology. The slides. I don't see the presenter screen.
Yeah. Okay. Great. So thanks for that introduction, Subhajit. I am really excited to be here and address your class. Compilers are a niche field, and it is something that is always relevant, and it is relevant in many different ways than we realize. And the objective of my talk today is to really introduce all of you, to the various ways compilers are used in the field. And one sort of disclaimer I would like to share is that that if you feel at the end of the presentation that you have understood fully about any of the topics that I have explained, then I would have failed in my attempt, because really these topics are very deep and require a lot of further study, and I would not be able to go deep into any specific topic. So it is, think of it like a broad overview and introduction, which will help you become aware of the different fields of applying compiler technology, and then you can hopefully that brings around some curiosity and some interest to dig in deeper. Okay, so with that I will start this talk. Okay, so in terms of agenda, we'll be covering these topics. So we'll first talk about traditional compilers, what are they, how do they work, and so on. We will abstract out of our understanding of our traditional compilers into certain key capabilities that compiler technologies provide us, and then we will see how those key capabilities can be used in many different scenarios other than the traditional compiling technologies, traditional compiler scenario. So we will look at static analysis, we will look at dynamic analysis, we will look at binary translators and runtime compilations. We will look at source-to-source translators and domain-specific languages. Now, each of these are individual sections, and what I will do is I will pause at the end of each section, and we can take some questions and have a short discussion if anybody would like to raise any points. Also note that this list is not exhaustive. There are lots of different fields of compiler that sorry about that. So there are a lot of fields of compiler technology that we have not, that I have not listed here, and just because of time and space constraints. So, but we can have offline discussion on any other area that you may want to know about. Okay. So with that, let me begin. So what is a traditional compiler? I think this is something that you are very familiar with. You may have used it already, and the basic idea is very simple, that you generate an executable binary from a high-level language input. So your high-level language input could be C or C++, and your output of the compiler is an object file, is a binary executable file, which really is encoded in the machine instruction set of the underlying hardware that the machine knows how to execute. Okay, so that's the basic idea. Let me. Okay, so common examples are Fortran, C, C++. I know that maybe many of you have never programmed in Fortran, but the reason Fortran is mentioned here is because Fortran was the first language for which kind of a compiler was developed for production industrial use, and the idea back then was that people were writing all their code in assembly, and Fortran compilers meant a huge productivity improvement for the programmers, because now they could write in a high-level language and be much more effective at their jobs. So there are many well-known compiler infrastructures, GCC, LLVM, Microsoft Visual Studio, and many others, and each one of you may have used some or all of them. In these compilers, optimizations tend to be a key area of focus, and I'll talk about why that is so. And there are several performance metrics that are used when we are talking about optimizations. One, of course, is how fast the generated code runs. right? That is your generated code quality or generated code performance. But also other factors matter. For example, the compile time, the time taken by the compiler, or in cases it could be the memory footprint of the compiler to be able to generate the final output code. In other cases, for example, in embedded systems or in smaller resource constrained environments, the code size could be a performance metric for the compiler, where you are evaluating how small the output binary is, and there could be various reasons why that is important. Maybe the memory size is small, maybe the iCache size is small, and so on. Often you would find that it is very hard to get all the parameters optimized to the large degree. There is often an engineering trade-off that you could get better generated code quality at the expense of higher compile times. And if you are not ready to spend that compile time, then maybe your generated code quality suffers a bit, right? So these performance metrics are often sort of at loggerheads to each other. And one of the key challenges in engineering highly tuned and production quality compilers is to trade off these sort of conflicting goals and still be able to satisfy a large number of your customers or users. Most compiler infrastructures are used, the popular ones are used by a very large user base, right? A key example is GCC. It is available on many different platforms, many different operating systems. It has capability to handle multiple languages, and it can generate code for multiple processor architectures. Now, in this environment, think about the job of the compiler writer. So the compiler writer or the compiler developer faces increasingly challenging tasks where they have to design optimizations in such a way that they are good for all inputs and bad for none, which is a very tough problem to solve. It is, in fact, in many cases, NP complete or NP hard problems. So as I mentioned, there is a very large user base for compiler software, and compiler software tends to be also very large and complex by itself, often running into very large code size and very difficult to prove that it is doing the right thing. For example, if you are going to use your compiler to generate code which would run on a mission critical or a safety environment, most modern compilers are very, very difficult to ascertain in presence of full-blown optimizations that they are correct under all circumstances. So they're very complex and very large software-based code bases. However, it remains true that there are very relatively small number of compiler developers, right? So it is a small number of people trying to, build this core system software layer for a very large number of people who are the end users of this. So that is sort of an overview of a traditional compiler use case. And on your right, what you see is a diagram which shows the different phases within the compiler. Don't worry about what these phases are. I will explain you each of these phases in greater detail in subsequent slides. But what is important to note is that there is a flow of events within the compiler, right? So you start from your input program, you perform your lexical analysis first, you do your syntax analysis, and then further down you process until you get to the object code. And all this while you have to represent your program in memory in a particular format, which compiler authors or compiler developers tend to call as intermediate representation, or IR. Okay, so that is the brief overview. Let me move on. So it's good to understand a little bit about the landscape or the ecosystem in which these compilers operate. Okay, so firstly, on the input side, right, what is the input to a compiler? It is a high-level programming language in context of traditional compiler software. But even within that, there are literally hundreds of input languages, hundreds of high-level programming languages. Some we use very frequently, like C, C++, Java, and Python, and things like that. In other cases, they may be specialized languages, or they may be research effort. It could be meant for example, safety critical work, that you have specialized languages. But really, there are hundreds of programming languages, and many different language types and paradigms, right? So you could have imperative languages, or you could have object oriented, you could have functional, you could have parallel programming languages, you could have languages with strict type checking, you could have languages without types, and so on. So a lot of diversity in the input side, right? Similarly, there is a lot of diversity on the output side. Many different processor types. So you know about CPUs, GPUs, digital signal processor, DSPs, and then you may not have heard of this term ASIP, but what this means is application specific instruction set processor. So these are like, let us say you have a custom application in some domain, and you want to build a specialized processor for that. So those are called ASIPs. So there are many different processor types, and there are many different architectural styles in which these processors are built. So your CPU could be a CISC style CPU or a RISC style CPU. It could have VLIW instruction parallelism, or it could be superscalar. There are things like SIMD, single instruction multiple data, or single instruction multiple threads, with GPUs are SIMD. So there are many different architectural styles, and one of the subsequent guest lectures that Balki from NVIDIA would conduct would talk about some of these architectural aspects. So, but the bottom line is here that there are a lot of diverse inputs and lots of diverse outputs, and the compiler has to sort of keep up with it. So one natural question that comes here is, what drives this diversity? Why do we need so many programming languages, and why do we need so many hardware processor types? And really, in my mind, the answer is that it is application needs which drive this diversity, because we have a very diverse set of applications, software applications, whether it be some application that runs on your banking stack, to some scientific application that is trying to do protein folding, to some financial, to some applications like games, 3D games, real-time 3D games, or or things like artificial intelligence and deep learning, things like self-driving cars, right? So the computer vision, right? So there are so many different types of applications that for each application, a programmer or a system designer might come to the conclusion that the programming languages that I have for this application or this class of applications is not sufficient and I need a new programming language, or a system architect or a hardware architect might come to the conclusion that the processors that I have today for doing existing application is not sufficient for this new class of application, so I need a new processor. So what this shows is that as our sense of what the important applications evolve over the years, the need for compilers to provide that programmer productivity at high level programming languages will continue to evolve, both on the point of code generation as well as in the sense of supporting new programming languages. Okay, so okay, before I go into the details of compiler phases, let me pause at this point and see if there are any questions or comments. Remember that you are on mute, so if you need to talk, please unmute yourself.
Sir, in general, which language is used to write compilers?
Yeah, that's a good question, and there are several efforts. People have written compilers in many different languages. Most production compilers themselves are system software, and like other system software, low-level system software, they tend to be written in C, C++, but that by no means is the only choice or even the optimal choice. So there are several efforts which have used other languages to write compilers themselves. Other questions? Let me move on. Most of the material covered so far should already be familiar to you, but this is just to set the context. So let's talk about compiler phases. Right, so we talked about the several phases. I'm going to try and describe what each phase does. So in the lexical analysis phase, we match lexemes by regular expressions. Okay. That means is that every language has certain tokens. It could be identifier names. It could be reserved keywords. It could be operator symbols and so on. So the first step of a compiler is to match these known entities using what is known as tokens. And you might encounter certain errors during this time. For example, if a programming begin with a particular symbol, maybe the @ symbol. For such a programming language, if you have declared a variable with the prefix of @ then it would at this point. Okay. The next step is, so this step of lexical analysis is generally pretty simple. And there are many tools to generate your lexical analyzer. For example, the most commonly known are Lex or Flex, and you can go read up about them, and you basically have to give a regular expression as an input to that tool. You have to define the precedence of those regular expressions and some actions and things like that, and the tool will generate the lexical analyzer for you. So that is lexical analysis. The next step is syntax analysis. And in syntax analysis, what you're trying to do is basically every programming language will have its context-free grammar, and you are really trying to apply the rules, production rules of that context-free grammar to ensure that the syntax tree that you build at the end of syntax analysis is correct. Okay, here what the output of this phase is an abstract syntax tree, also or a parse tree. There are certain minor subtle differences. I will not go into that, but basically, to ensure that the rules of the language and all the inputs in your program form valid sentences as per the rules of your context-free grammar. That is the objective of syntax analysis, and the output or outcome of syntax analysis is this parse tree or abstract syntax tree. And here, for example, you might encounter a different type of error. So maybe your programming language says that no arithmetic operation can be performed on string literals, right? So you might get an error based on that. Then next comes semantic analysis, and when you are doing semantic analysis, what you are trying to apply the rules that define the meaningfulness of that program. So for example, if integer variable cannot be assigned to a floating point variable, and that's the rule that is there in your programming language construct, then the semantic analysis would catch it. It is still a legal sentence as per your grammar, but the semantic rules which are outside of your grammar are applied at this point and checked for. And what you would get here is a legal, as per the semantic rules, a legal AST or IR. Certain compilers at this stage would also convert their AST into 3-address code or linear IR and try to use that for the subsequent phases. Finally, you come to the first three phases, lexical analysis, syntax analysis, and semantic analysis, is known, commonly also referred to as the front end of the compiler, and the optimization and code generation phases are referred to as the back end. But all these terms and terminologies, I have not quoted the sort of pedantic or theoretically accurate descriptions here for sake of brevity. A full-fledged compiler course would do justice to many of the terms that are mentioned here. So coming to optimizations, you end up doing two distinct activities during program optimizations. So first is program analysis. And in program analysis, what you're trying to do is you are trying to discover information about the program. So you're trying to understand the program, you're trying to understand programmer intent, and discover information. Such discovery of information could be ad hoc in nature, like you could, identify how many loops are there in my program by walking through your AST or your intermediate representation. It could also be much more advanced. There are techniques like data flow analysis and many other infrastructure which allows you to discover other type of information about the program, which is much more mathematical, has a solid theoretical basis to it. Again, you really need to take a compiler course to understand some of those details. But the outcome of this is that you need a program information. You produce information about the program, which is what I have shown here. And some examples of such information is about, for example, liveness information or available expressions and so on. The second phase is after you have discovered some information about the program, you can transform the program into an alternate program which hopefully is functionally equivalent to the original program. So this is what we would normally call as the optimized program. So for example, if your program analysis discovered that a certain basic block is unreachable, that means it was it is guarded by a condition which is always false, then what you could do is you could remove that block of code because you as the compiler have been able to prove that this the control flow will never reach this block of code, and that is what we call as dead code elimination optimization, and what you get is an optimized program which does not have that block of code. Finally, the next phase is code generation, and this is where essentially you map the optimized program into the target language, which in context of traditional compilers is generally a low-level machine language. And the output of this phase is of course the object code that can then be further linked and loaded and executed. We have a subsequent session by Girish, which is going to talk about all the program execution environment, things like linkers, loaders, etc. And that's where you can get to hear more about that. But during the code generation phase, normally compilers do a lot of very custom optimizations. Most of the problems here are NP complete or NP hard, so there are no perfect solutions. But broadly speaking, the compiler is involved in what is known as instruction selection. That means that you are taking nodes of your high-level AST or high-level IR and selecting an instruction that can map, that exists in the underlying hardware and can map correctly to the node in your program representation. Then you are doing resource allocation. It could be register allocation. It could be other types of resources depending on the hardware. There are a variety of resources that the hardware might expect that the programmer or the compiler have already allocated. And then there is also the phase of instruction scheduling, which is all about discovering parallelism, handling latencies, and optimizing the program. So a lot of interesting things go on within each of these phases, and but right now in today's session, I will not be going into all the details here, but we are going to do an overview. Okay. So in terms of key capabilities, so I talked about various phases of the compiler. It makes sense to look at what essentially is the compiler able to do with that capability within that phase, right? So lexical analysis is nothing but the ability to recognize tokens from an input. Okay, so let us remember this, that we have some software which can recognize tokens from an input, and as you can start seeing that this ability to recognize tokens can be used in many different situations for many different purposes. Syntax analysis is the ability to analyze conformance to a language grammar. As long as the input to a software is structured, right? So computer programs are always structured. So it has a grammar, and syntax analysis gives you a way to know whether my input adheres to the expected structure or expected rules of the grammar, right? So that's a useful capability to have that I can use in many different situations other than generating code for C or C++ to a machine language. Semantic analysis is the ability to reason about meaningfulness of the input program as per rules of the language, and we'll go into some of the details there. Intermediate representation is nothing but the ability to represent the input program in various forms, and intermediate representations tend to be very challenging because they need to have different characteristics for different phases of the compiler. If you want to do high level analysis and high level restructuring of your code, something like an AST would be really useful. But if you want to do instruction scheduling, then linear 3 address code is perhaps more suitable. If you want to do instruction selection, maybe a directed acyclic graph, DAG, is more suitable. So this term intermediate representation, when you dive deeper into it, could mean different things for different phases of the compiler. And then program analysis is really interesting. It is the ability to discover certain properties about the input program. And that's always useful, as we will see in subsequent slides. Optimization, as you can see, is very profitable, and this profit function of what is a better program can change from situation to situation. Say you are done your program analysis, you would do a different set of optimizations. But if you are optimizing for generated code quality, then you might do a different set of optimizations. For example, you may do a program analysis phase to discover whether your loop can be unrolled, but you may not choose to unroll it if you are optimizing for space, code size. And finally, code generation, as we talked about, is very complicated, and it is, but at a higher level, at an abstract level, it is the ability to translate input programs to an alternate language. Okay, so that covers the first sort of section of my talk. I would pause here for any questions anybody would have.
Sir, do the compilers give the user option to skip optimization? Because in some cases the programmer might not want the optimization.
Yes, for some programmers, the decisions made by the compiler could be counter to their purpose, and often compilers come with a sophisticated array of knobs and controls to for the user, particularly the advanced user, to sort of guide the compiler in taking the decisions that they think is right. Okay, so but in any case, for most compilers, if they support debugging of the executable generated, then they also support a mode of compilation which does no optimizations, because debugging of code in presence of optimizations is a very difficult problem to solve. So most compilers would have an option which disables optimizations, and often that is used in conjunction of with producing debug code. Any other questions? Okay. So with that, let's look at this. So the motivating question that I would like to ask is that we have these different capabilities: the capability to recognize a token, capability to apply grammar rules, capability to do semantic checks, discover program information, transform the program and translate it to another language. So the key question is, what else can I do with these capabilities? Where else can it be useful? And that is where I'm going to now branch off from the traditional compilers that you are used to probably seeing, to some different areas of compiler technology where some of these core capabilities are reused either in exactly this, in a slightly modified way to suit the needs of that specific problem. So the first one I'm going to talk about is static analysis and static analysis of source code. Here source code means a high level language program. Remember that all of these terminologies say they sometimes have kind of a layman definition and sometimes have a very pedantic and accurate definition. So the literature that you will find outside it tends to confuse and have a lot of interpretation around these terms. But static analysis can be performed on both high-level source programs. It can be performed on any intermediate representation. It can be performed on binary objects as well. But we'll talk about static analysis right now in context of source programs. And the capabilities of the compiler that this uses is the ability to recognize token, apply grammar and semantic rules. That is your common compiler front-end part. And then it also uses your ability to discover information about the program. Okay. So what static analysis tries to accomplish is it tries to generate information about the execution of the program without executing it. Okay. So this statement will become clear in the subsequent slide, but what it hints at is that we are trying to discover properties that would hold true when we are executing that program. But we are trying to do it in a manner that does not require us to execute, generate code for it and actually execute the program. The interesting thing about static analysis is that it is not driven by test cases. Okay, so it is not limited by how many tests you can run on your application software that you have compiled. It is driven by analysis of the source code of your application software. Okay, and some of the key problems that are solved are firstly detection of defects. I think this is one of the common areas where static analysis is used. Nowadays, increasingly security related problems. It is, you could say, some of them are a subclass of defects. But they are very key and very important for many software. So that becomes a part of static analysis. You could use static analysis to discover performance issues. And of course, you can use static analysis to also enforce certain syntactic or certain, I would not say really syntactic, but certain conventions of how your input program has to be written, which is not really part of the grammar, not really part of your semantic rules, but still in very large projects, often there are some kind of coding conventions. Or certain safety standards might have certain coding conventions for purpose of readability and so on. So enforcement of coding standards is also an area where static analysis is used. As I mentioned, it relies on the compiler front-end phases, which is lexical, syntax and semantic analysis, and it relies also on IR construction and program analysis. Important to note that input to your static analysis tool could be a source code or could be a binary object code. However, in this talk, we will mostly discuss the source code, static analysis of source code. Okay. So what are the examples? What kind of errors or situations that the static analysis can help us discover? Okay. So you may already know about buffer overflows. I'm sure you know what uninitialized variable access means. That means you have not initialized the variable, but you're trying to read it or trying to use it in any way. Resource leak refers to you allocating memory which you forget to free, and that memory is lost forever. Is considered as a memory leak. Sometimes there are unsafe or improper conversions between types, which can we talked about dead code previously. So let us look at some examples of this. So if you see the code on the right, so what this does is it calls malloc and allocates a buffer, and it tries to copy from another buffer into this buffer called buff1, right? So do you see anything wrong with this? Would anybody like to call out anything wrong with this? Can this program, when executed, malfunction?
Sir, we don't know about the sizes of the buffers, buff1 and buff2. So buff2 can be more in size than buff1.
Correct. So buff2 can be more than in size than buff1, but that's a property that you will discover when you run the program, right? However, what static analysis tells you is that these two buffers can be different, and it can flag an error or flag a warning saying that, hey, I have discovered something that is potentially unsafe, and you can use that warning to go fix your code. Remember that while running this piece of code, there has to be many more preconditions before you discover this error. Firstly, your test case input to your application has to be such that this part of the code is executed. Secondly, the size of the buffer has to be actually larger for the problem to occur, and so on. However, static analysis without use of test cases can flag this error, okay, or flag a warning. The second example is, if you see the code on the right, you see two variables are declared. One of them is initialized with some value, but this variable A is being used in this return statement without having been initialized. Now, a compiler is usually very effective in discovering such information. So it can discover this information that the variable A was uninitialized on some path by the time it was used in this return statement. And that program information that it has discovered can be used to guide the end user, saying that, hey, you have a problem here, right? And now the end user can choose to heed that warning and change their code to a safer code, or they could ignore it at their own peril. If you look at this example here, you have a malloc which is assigned to this pointer. The return value of the malloc is assigned to this pointer. There is a use of that pointer, and then the function simply returns. Now what is happening here is that the allocated memory is never freed, and the control has exited out of this function foo. So because the control has exited out of this function foo, the variable A is no longer accessible, because it was a local variable, to any part of the code outside of this function foo. And as a result of that, this memory that was allocated has been lost forever, and would end up being a memory leak, which, as long as the application runs, will continue to waste that precious resource. Now, memory leaks are very troublesome, and a lot of people would go to a lot of extent to avoid memory leaks, because they want to use their hardware and hardware resources to the most effective way possible. So a static analyzer can actually easily detect this situation, where it would say that, okay, the variable A is live all the way, and it would need some additional technology to discover that, it should have been used in a free, but it wasn't used in a free call, and in a combination of compiler-like analysis and some recognition of standard library routines or certain API calls, it can discover this information by analyzing the source code without having to run this program. Then there are other examples of type conversion. There are in fact two errors here. One is that you are assigning a floating point literal to an integer variable that would lead to loss of information. And secondly, you are assigning an integer variable to a character variable, which would also lead to loss of information. Static analyzer will be able to flag both these as warnings and tell you that you have a problem. This piece of code is slightly complex. I would let you take a moment to go through this. But what you see here is that there is a value of 10 being assigned to the variable b, which is then multiplied by 2, and you get the value of c, and that is used to compute the value of a, and then there is a comparison operator. Now, what a smart compiler should be able to do is it should be able to deduce through a combination of program analysis and program transformation that the value of a will always be 30. And thus, this condition will always evaluate to false. Okay, by the way, I also see another typo, so ignore that. But this condition would always evaluate to false. And because it would always evaluate to false, the function foo will never be invoked. And this is a discovery and conclusion the compiler can reach, or the static analysis tool can reach without having to run the program, and it can flag this as a problem to the user, saying that, hey, did you really intend to write the code this way, or are you do you have a bug that you would like to handle? Coding errors, and this is where the typo comes from, sorry. So you see here that there is a bit of coding error here. So you see the semicolon here, which completely changes the meaning of this if condition, and that is something a static analysis tool will be able to discover as well. And finally, there will be coding conventions, like your project might say, I want to follow this type of naming variable, like small letters followed by the when you have two words, the first alphabet of the second word should be capital, or I want an underscore separator, whatever. So some convention there, there can be very complex set of rules for conventions. There can be simple rules for conventions. But static analysis can often discover such violations and help solve that. Okay. Yeah. No. We want to next talk about static analysis. How does it work? Okay. So basically the lexical and syntax analysis part remains same. So the compiler front end part would kind of remain, but you add additional semantic rule checking for type checks. So in the previous example, we looked at, in the previous slide, we looked at, say for example, this error where we are saying that there is a loss of information from moving data from an integer into a character variable. So this information discovery requires additional checks in the type system, and that can be thought of as additional semantic rule checking. Also, static analysis requires a fair bit of program analysis, which may involve analyzing the control flow of the program or analyzing the data flow of the program. So again, I would go back to the previous slide, and I would say, maybe pick on this example. So the fact that this basic block is unreachable, this call to foo is unreachable, would involve some kind of both data flow and control flow analysis, and so also things like propagating this constant of 10 to this location, propagating the value of C all the way down to here, flow analysis, as well as in this particular case some transformations as well to discover things like constant folding have to be done in order to finally get to the value of A. Okay. Then static analysis can be very interestingly also extended to API aware checks. So if you are, let's say, working with a particular library or a particular middleware software, and those API calls have some kind of rules associated with it, then you can build a static analyzer to check that whether when you are making the call to those API routines, whether you have done the right thing or not, right? And often such rules are not part of your standard programming language rules, but really they are rules emanating from the semantic or the functionality of those APIs. For example, we saw this this little code snippet where the use of a free here. So see, the term free is not really part of the programming language. The token free is not part of our C programming language, but a static analyzer can be made more intelligent by recognizing that this call to free is a call to your standard library routine, and it has this special semantic of freeing memory, right? So with that API aware knowledge, it can do additional checks and say that, okay, this memory has been freed, so it is not a leak. Okay. There are other aspects like model checking and formal verification that is also involved in static analysis, but they are fairly advanced steps, so I will not go into details of that. But I do want to cover this aspect of false positive. So remember how I explained that you do not need test cases and you don't need to actually run your application in order to do static analysis. That has a downside. And the downside is that sometimes it will report certain things as issues which you as a programmer may know that they are not issues. And here is an example of that. So here, if you look at the first if block, under some condition cond 1, the x variable x is assigned a value, and subsequently under some different condition the variable is used, right? Now you as a programmer might know that all cases when the second condition is true, first condition is also true. This is the information that you as a programmer know because of the nature of the program and the nature of the algorithm that you have written. However, static analyzers will see this code and say that, hey, there exists a path in the program in which the value of x is uninitialized, right? And that path is primarily when condition 1 is false, but condition 2 is true. And the static analyzer is unable to tell you that this path will never occur or not occur. So it will give you an error which may happen during execution or which may not happen during execution. Such problems are known as false positives. That means it is telling you that something is actionable for you as a programmer to fix. However, it is a false indicator because you as a programmer know that this situation would not happen during execution. So that brings me okay, so that brings me to the last slide of static analysis. So these are the static analyzer tools that we have. There are literally, if not 100, tens of them out there in the market, and I cannot cover all of them. But usually static analysis tools tend to be language specific. So you might have a static analyzer for C, or you might have static analysis tools for C++, you might have a different one for Java, and so on. They are also different in terms of how much capability they provide to their user in terms of extensions. So some tools are fixed checkers. So they have a well-defined set of checkers, and that's all that they check for. Some other tools are more extensible as an infrastructure. That means you as the as a developer, you could add additional custom checkers of your own into the existing infrastructure of static analysis. Okay, and some of the examples of the tools are, one is called as Clang Tidy. This is part of your LLVM compiler suite. I would strongly encourage all of you to go check this out. It's a really nice tool. It has lots of checkers, and it is an extensible framework that you can do. You can extend to do some really fun stuff. Okay, so you can check for things like how many variable names. So here is a thought experiment. How many people in the class use the variable I as their program, as their loop counter, right, in class assignments? So that's a tiny little static checker that you can use and discover some property of your program. Okay. Then there are tools like Lint, Eclipse, and many other commercial tools. I think on the commercial side, Coverity is one of the popular ones. But there are really many tools out there which do static analysis of programs from the point of view of security, from the point of view of safety, for just programming, compliance. Certain platforms like Android has their own rules about what kind of code you can submit to Android code base, and there are static checkers to ensure that those rules are maintained, and so on. And also there are some really advanced formal verification tools, like in context of languages like Ada, which are used for specialized safety or mission critical software. So that brings me to the end of the static analysis section. So at this point, are there any questions? Have I bored everybody already?
So Dipapan, so there is a huge variance in the sort of effort that is required to write different static analysis tools corresponding to different properties. Mm-hmm. Like maybe you can comment a bit on that. Like for example, writing a small checker in something like Clang Tidy might be for I would say like shallow properties, which are much more easier to write. Then maybe something more sophisticated for maybe functional correctness or something that you could write for. Maybe you create a model checker or something like that.
Yeah. So definitely, any kind of discovery of information for model checking or any other formal ways of proving functional correctness of a program is very advanced, and it requires not only static analysis but other methods to be understood, and also it depends on the kind of code infrastructure that you get access to, right? So something like Clang Tidy has the necessary infrastructure to normally do checks on your AST. Maybe in some cases it can go a little deeper than that, but if you want to do checks on that involve optimization details, or even further down below in the compiler stack, then it becomes more and more complicated. And I guess the base infrastructure that is needed to do your advanced static analysis can be a factor that limits how much you can how successful you are.
There is another question from Aman. So he's asking, what are the things you look at to choose a static analyzer for an application?
Okay, so there are many parameters. I think one, as I said, it is language specific. So definitely certain choice of static analyzers are eliminated. Like if you're working with Java, client ID might not be the right choice for you. So that is one set of filter. But more importantly, it is to determine what is it that you are trying to achieve, right? So let us see, if you look at security, right? So there are a lot of security issues that are publicly disclosed, and people are expected to avoid those security issues. And so there are many different standardized security patterns, and some tools have those patterns already built into them. So if you're looking for security checkers, then you might want to choose a static analyzer which supports those patterns. Sometimes coding conventions come because of, as I said, a larger program objective, like you are contributing to Android source, and Android has a certain set of rules. So you might want to choose a static analyzer that is already aware of all the rules of Android submission, and so on. So that is one. Those are one set of factors. But then the other factor that you want to look at is the extensibility of the infrastructure, and how much effort it takes to extend the infrastructure for your custom use case. And I would also say the number of false positives it yields, right? If you have a tool that is very noisy, that means it flags a warning on every line of your source code, then such a static analyzer will probably be very, it will be hard to use, because you would not know what is the real issues. So there is always, in some sense, some decision making that is needed to determine, which kind of static analysis warnings are more in priority or in severity, in what kind of impact that they might cause, and which ones are lower priority. So you might want to choose a tool that allows you to distinguish based on those priorities, so that you can, let us say you have a source code base of 100,000 lines of code, and the static analyzer generates 50,000 warnings. You want to choose a tool which allows you to segregate based on priority and impact of that problem, and so that you can go resolve them in a way that is practical, rather than having to visit every line of your source code.
So I have another question. So nowadays there is a lot of use of like even machine learning and deep learning techniques for static analysis. Like
Correct.
using things like code to vec or something, you get embeddings of your source code and then try to reason, do like statistical analysis over them. So how much of that is sort of prevalent in industry, sort of, or is it already circulating?
I think this field is very sort of emerging. People are trying all kinds of things, and I guess that when the cost is very high, like say for example, if doing this neural network based